Finished my general announcements and shared commentary about the Canvas calendar, the highlight of which is the free response challenge is due tomorrow, dead on Thursday. Students will receive a take-home quiz for section 1.2. They're encouraged to work together on that, but not copy. That'll be due on Friday. Okay. Now, last class, we ended on, well, we only spent about 10 minutes because we had the special like half day schedule for Clarksburg Light Day. So really all we did was we scratched the surface on, we talked about dot plots for about 2 seconds, and then we talked about stem and leaf plots. Today, we're going to wrap up a little bit more about stem and leaf plots and then talk about histograms. So with the first stem and leaf plot, we pointed out several different issues with this first example. The leaves are out of order. I don't like the use of commas. The data is way too compacted. It's not spread out, so you can't describe shape. There's no key. The next stem and leaf addressed most of these issues. It brought in a key, it removed the commas, it ordered the leaves, but it did not stretch out the data so you can actually see the shape. So then we looked at 3 potential options for how do you split up the data. And what we talked about was the one in the middle is not a good option. The first option, every single stem has exactly 5 possible numbers that can fall into it. The very last one, which splits the stems 5 ways, that's a lot of splitting, but it's still fine because every stem has 2 possible numbers that fit into it. However, the middle one is not a sort of uniform split. For example, the first 6 has 3 possible numbers, the second 6 has 3 possible numbers, but the third 6 would end up with 4 different numbers. The whole idea behind building a quantitative data display is very often to see the shape. And if you distort the shape artificially by forcing more data into a certain bin, you're kind of disabling your own desire to see the shape of the disability, or see the shape of the data is what I meant to say there. Okay, go ahead and turn the page. That is a very brief summary of what we did last class. So let's look at a few examples because one of the things that I mentioned about building a stem and leaf plot is a rule you have to follow is 1 leaf per data point. Okay. So the first display and the second display break that rule. And I'll get to how to address that in a minute. The third display has exactly 1 digit per leaf. So that's perfect. That's following that rule. The other thing I mentioned in last class is the number of stems you use is totally up to you. You can have 1-digit stems or 2-digit stems or 3-digit stems. The only thing you can't do is skip stems. You have to count 1 by 1 by 1, kind of like you would a dot plot. Okay. So the weights of cattles in pounds are provided below. Multiple examples of possible stem plots are shown below. Complete each list that follows, which explains what is wrong with each stem plot option. So the first one says, I'm going to treat the very first digit as the stem. Now, I want you to notice, if you look at this list of numbers and you only pay attention to the very first number, how many different numbers are there? I saw a number of you put up fingers, put up 2 pretty fast, which is great. If you look at every one of these numbers, every one of them either starts with a 1 or a 2. So if you're going to say, you know what, I want to treat the thousands place as the stem, then you're going to end up with this display. Okay, now there are a couple issues I have with that. What's an issue? Yep. The commas. I don't like the commas. What else? Yep. Multi-digit stems. Absolutely. There's one other issue. It's the slightly more subtle one, but we did address it last class. I got the commas. So we got the commas and we got multi-digit stems. It's too compacted. All the data fits into 2 little bins. Okay, so you don't have enough bins. You're not going to be able to see shape. You're using commas, which I don't like. And you have multi-digit leaves, which I also do not like. Okay, so for several very, very obvious reasons, it's probably not the best idea to use the thousands place as the stem. All right, fine. Now, let's look at these numbers. And you know what? Just so we can see them a little more clearly, I think I had them copied somewhere. Oh, it's down there somewhere. Maybe it's that. Ooh, there it is. Those were the numbers. All right, can kind of fit them on the screen. All right, let's say you're looking at the first 2 digits. So now you're looking at the hundreds place. What is the lowest number of hundreds on this list? What was it? 15. Okay, the smallest number has 15 hundreds. What is the highest number in terms of hundreds? 20. 24, 2400. So if you're going to say, you know what, I'm going to treat the first two digits as a stem, that's where you're cutting it off. You have to start at 15 and you have to count one by one up to 24. Got it? Now, this to me clearly addresses one of the issues. It clearly addresses the fact that there aren't enough bins. It stretches out the data. It still has two pretty glaring issues. It's still using comma. It's still got multi-digit leaves. All right, we have one third and final option. You know, you can either cut off the first number, or you can cut off the first two numbers, or you can cut off the first three. So now we're talking about the tens place. Okay, the smallest number has 157 tens. Does that make sense? And the largest number has 248 tens. You want to cut it off at the tens, be my guest. But if you're going to do this correctly, you have to build a display that starts at 157 and counts by ones to 248. I'm not interested in that. Okay, now this one solves the repeating issues that are here. We no longer need commas because every leaf is a single digit, but now we kind of have created the opposite problem that we had in the first display. The first display, the data was too compact. Now we've spaghettified the data. Does that make sense? We've just like stretched it to oblivion. And now all we're going to have is way too many bins with like a few random data points just all over the place. So you're not going to see shape that way either. Okay. So the lesson I want you all to take from this is that when you're building a stem plot, you really have the freedom to choose where do you want to start your stem. But there's some logic and reason that goes into which one works the best. You know, and here, clearly, the best option is to cut it off at the hundreds. But now we need to address the fact that we're not supposed to use commas and we're supposed to have single-digit leaves. So this is where the problem down here comes in. If used, rounding or truncating omit a small amount of information. One reason keys are so important is because they allow a display to be clear about this loss of information. Part B at the bottom says complete the stem plots for this data, including the key, using each option described below. Option 1, these are the two most common tactics people will use to reduce two-digit leaves to one digit. Okay? So we're going to take this data and we're going to talk about the truncating option, which is by far my preferred one because you don't have to think. Truncate by ignoring the last digit. So what you can do is you can say, all right, I've decided it is clearly best to cut these numbers off at the hundreds place because then I have a display that goes from 15 to 24. Got me? But I can't record both of the remaining digits as leaves because you're not allowed to have multi-digit leaves. So you know what I'm going to do? I'm going to do the lazy thing. I'm just going to ignore the very last digit. I'm going to pretend like it's not even there. And I'm going to record a 15 followed by a 7. I'm going to record a 16 followed by an 8. I'm going to record, we need 3 numbers after the 17 because we have a 17.5, a 17.7, and a 17.7 again. So I'm going to record 577 after the 17. Everybody with me? Okay, prove it. Take a minute and see how many of the digits you can fill in yourselves. Now, here's where the key becomes really critical. If you're going to read this display incorrectly, then you're going to say, this must have been a cow that weighed 1,570 pounds. And my response to you is, yes, that's one of many options, but that's not the only option. Because all we've done in this display is we've completely ignored the last digit. So that last digit could have been a 0, but what else could it have been? A 9, or I heard a 4, or a 5, or an 8, or a 2. Everybody with me? So your key needs to explain that if you see a 17 followed by a 7, what that means is you had a cow that weighed 1,770 something pounds. Does that make sense? So the smallest that cow could have weighed was 1770. The heaviest it could have been was 1779. Now, for anyone who's not totally clear on that, okay, here's my little visual cue to help you out. Okay, if you are just chopping off these numbers, this is basically what we're saying. That if you're just going to ignore the singles digit, then a 17 followed by a 7 is a cow anywhere in this range, because when you ignore the last digit, you end up with a 17 followed by a 7. Does that make sense? Question. Now, let's not get lost here. We started this page by saying we have the freedom to decide where we want to cut the stem off. Okay. But we have to consider the number of bins that that creates. And if the ideal choice would leave you with multi-digit leaves, you need a way of reducing that to a single digit leaf because that's the rule in stem and leaf plots. So here's the other method. This one is not my favorite one because it, to me, makes something that could have been simple a bit more complicated. Okay. And that is rounding. Just round to the nearest tens place. Okay. So now what I'm going to do is I'm still going to cut this off at the tens, okay? But what I now have to ask myself is, if the next digit is a 7, I can't just write 7. I have to decide, should that 7 stay a 7 or should it round up to an 8? And because that 7 is followed by a 5, it would round up to an 8. And then if you look at the next number, okay, it's a 16 followed by an 8, but should that 8 stay an 8 or should it round up to a 9? Well, it's followed by an 8, so I'm going to round it up to a 9. Now, with the next bin, and this is the last one I'm going to do for you all, 2 of the numbers are going to be the same. In the previous display, it was 577. Well, now it's not going to be 577 anymore. The 5 stays a 5 because it's followed by a 2. The first 7 stays a 7 because it's followed by a 3. But the next 7 is going to go up to 8 because it's followed by an 8. 5 or higher, you round up. So now 577 turns to 578. Okay, take a minute, finish that display. All right, so there's the finished rounding display. Now, I said before, I gave this little visual clue on the right side, what the possible range is if you are truncating. You know, you just chop off the last number and it follows by a 7. So it's 1770 to 1779. But what if we're rounding? Can anyone volunteer? What is the smallest weight of a cow that would result in recording it as a 17 followed by a 7? The smallest weight that would result in that. Perfect. 1765. Because if it's a 17 followed by a 6, you have to round that 6 up to a 7 if it's followed by a 5 or more. So 1765 is the smallest weighted cow that would be recorded as a 17.7. Can somebody else volunteer the heaviest cow that would still be recorded that way? 1774. Because if you already have a 7, as long as the number after that 7 is not 5 or higher, it's going to stay a 7. Now, for anyone who's not totally clear on that, here's essentially what we're saying. This is your range of cows if you are rounding, because 17.6 with a 5 rounds up to 17.7, and 17.7 with a 4 stays a 7. Does that make sense? Okay. So your key needs to make that clear. And I'm telling you now, there's a problem on the take-home quiz that people constantly mess up because they're asked to provide a key and they don't give the range. They just say 17.7 means a 1,770-pound cow. You'll get partial credit because there's still logic in your answer, but you're not going to get full credit because you're not admitting that there's a range that that stem and leaf could represent. Questions? All right. Now I'm going to pre-warn you on this page. I'm going to move a little fast here because I want to give you all a chance to build a histogram today. I really do want to get to 1.25 or 1.26. All right. Now, this is actually something that you will see in a homework problem. It's called a back-to-back stem plot. It looks fancier than it really is. And if it helps you, you could almost imagine, you know, I would say that we're probably at a point where if this was the only part of the display, then fine, we got it. But it's a little awkward to have the numbers listed in what feels like reverse order on the other side. Does that make sense? Because it's like the lower numbers start in the center and then move out. So if it helps you to imagine that exact same data but flipped, fine, more power to you, whatever. Okay, like now it's in numerical order, but you know, anyway. So another common use of stem and leaf plots is to create what is called a back-to-back stem plot. Below is a back-to-back stem plot of the weights of 65 sixth graders and 64 seventh graders. Complete each key below. Each set suggests a different procedure in making the display. Now, by the way, the thing that stands out to me right away, and this probably shouldn't shock us, if you had to estimate where is the center, and remember, this is like a 68-pound seventh grader, 83-pound seventh grader, 116-pound seventh grader. Everybody got me? If you had to estimate where is the center of the seventh graders, I'm hearing between 9 and 10, somewhere in there. So can we kind of agree that seems like a reasonable center? All right. What about for the sixth graders? I heard somebody say at 9. Can we agree that seems reasonable? So if I asked you to use these displays to compare these two groups, one of the things I guarantee I'd be looking for is that a reasonable estimate of the centers, like the sixth graders seem to be centered around maybe 95 pounds. Seventh graders seem to be centered around maybe like somewhere, well, that's like 90 pounds and this is like 95 pounds. And what that means is seventh graders tend to weigh more. That's a comparison using visual displays. In any case, if you are not rounding at all, remember the sixth graders are on the left, the seventh graders are on the right. If you see this 8 with a 7 in the middle, the 7 is a stem for both of them. This is a 70-pound person for both of them. It's 78 pounds for the sixth grader and 75 pounds for the seventh grader. This is literally just me teaching you how to read a back-to-back stem plot. Now, if you're told truncating was involved, then for the sixth grader, that's 7, 8. Well, that just means they were 78 point something. They truncated something. So it could be a 78 point, and it says if the 10th place was truncated. So it could be 78.0 or 78.9. So somewhere in that range. Okay, same thing with the sixth grader, but remember it's a 7 stem with a 5. So there's 75.0 to 75.9. Okay. Now, if the tenths were rounded, this is where it gets obnoxious. Can anyone tell me what is the lowest a sixth grader would have to weigh in this case? Yep. 77.5, because if it's 77 followed by 0.5 or higher, you round up to the 78. What is the most that sixth grader could have weighed? I heard 78.4. I like the 0.4. Yes, perfect. So 0.4 would not round. Okay. Now, how about for the seventh grader? We're going to see the same thing, except now it's centered around 75 pounds. So the lowest would be 74.5. The highest would be 75.4. And again, I like the 0.4 because that's what prevents it from rounding up. Question. That's a crash course on how to read a back-to-back stem plot. All right, last thing before I give you all a chance to build a display yourselves. The back-to-back stem plot below shows the heights of randomly selected high school students, 21 non-seniors, 19 seniors. Find and compare the medians of non-seniors and seniors. Now, medians is a word that hopefully we will recognize, but if you are the median person, what that means is 50% is under you and 50% is over you, okay? So we're going to find and compare the medians. Now, we're told we have 21 non-seniors. Let's try to take this slowly because this can be confusing. Imagine I am one of those non-seniors. And imagine I am the median person. Okay, we're talking about the heights of a bunch of people, and let's say I am the median person. If I'm in a group of 21 people and I am the middle person, how many people are shorter than me and how many people are taller than me? In other words, there should be an equal number on both sides. So how many people are on each side of me? 10. 10 over there and 10 over there, and I'm lucky person number 21. Does that make sense? So on the display, the way you find the median is either start at the top and count down to the 11th data point, or start at the bottom and count up to the 11th data point. You skip the first 10, and then you end in the middle. Does that make sense? And you should end up at the same spot. If I start at the bottom counting up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and that first 5 is the median, because that was the 11th data point going up. If I had started at the top counting down, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and that 5 is the middle. Does that make sense? Prove it. Find the median of the seniors. All right, so I want to make sure everybody can follow this as well as possible. If you have 19 people, because that's how many seniors there are, and I'm one of them, I'm the median person, that means there are 18 other people. 9 of them are on my right and 9 of them are on my left. So I am the 10th data point, whether you're coming from the bottom up or the top down. Does that make sense? So if you're going to go from the bottom up, you count the first 9 and then stop at the 10th. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and that first 0 is your median. If I counted down, and I heard some of you arguing about, do you count from the inside out or the outside in? It's a little weird because if you're starting on the high side, you actually have to start on the outside counting in because you're doing the highest numbers first. So it's 1, 2, 3, 4, and then again, starting on the outside, 5, 6, 7, 8, 9, and I stop because the 10th data point is my median. Okay? Yes. So the thought process to be able to answer this question is you can't compare the medians unless you can find them. So you have to at least get to this point. You have to realize, okay, 65 is the median for non-seniors, 70 is the median for seniors. But then you can compare them. And you can say, based on the medians, seniors tend to be taller. And I'm telling you now, if you're asked to compare, I guarantee you I'm looking for comparison language. Do not list features when you're told to compare them. Do not say non-seniors median is 65, seniors median is 70, and think you're done. All you've done is list them. You haven't compared them. Yes, sir. All right. Next one says find and compare the ranges. Okay. In this case, range is defined as the minimum minus the maximum minus the minimum. So for non-seniors, the tallest one is 76 inches, the shortest one is 57 inches, and the difference between those is 19. Okay. How tall is the tallest senior? 80 inches. Okay. That's 6'8", by the way. So that is indeed a very tall senior. How tall is the shortest senior? 61. And what is 80 minus 61? 19. So they end up matching. So the first summary statistic, the median, seems to suggest that their centers are different. And that difference in centers suggests seniors tend to be taller. No shocker there. Okay. But then the second summary statistic, the range, which is a measure of variance, it's a measure of change or spread, is equal. So what this seems is, all right, well, based on the ranges, which are both 19, heights of both the seniors and non-seniors tend to vary about the same. We're only going to get through part A of one other problem, then we'll call it a day. So far, what you've gotten in section 1.2 is a crash course on dot plots and stem plots. We're going to start on a very surface level with histograms today, and then we'll practice more of that tomorrow. Okay, now, if you turn the page once, you're basically getting, again, a how-to page. We saw this with dot plots. We saw this with stem plots, and I would recommend that you read this on your own time. I'm not going to read through this in class. Instead, I'm going to get right into it. Now, you can go ahead and look at this page. But again, I want to remind you of something before we actually get to this. And I'm going to use data that has nothing to do with this exact problem. It's you know, a different data set. This is actually a data set I used when I taught intro to statistics. I've never done that at Clarksburg. I taught it at Einstein, though. What this basically showed was from 2011. I'll zoom in on this. It showed from 2011 the percent of residents of all 50 states, and I don't know if DC was not included here. So for all 50 states, the percent of foreign-born residents. Okay, so we live in Maryland. That was at 13.7% in 2011. So 13.7% of Maryland's population was foreign-born residents. Some of the lowest states, I see a 2% for Montana. One of the higher states, I see 22% for New York. Okay. Now, if you wanted to make a dot plot with this data, this is what it would end up looking like. Okay. So you've got a ton of states that are below 5%, and you've got one state that's up there at 27%. I think that was California. It was California. That's what I thought it was. Yep. 27%. Okay. You've got a few states in that 15 to 20 and 20 to 25 range. Now, what I told you last class was a histogram is just like the lazy man's dot plot. I don't want to have to put a dot for every little data point. That's too obnoxious. I'd rather just set up ranges, and you can decide what you want those ranges to be. I decided on 5%. And you just count how many dots go into each range. And that is what creates your dot plot, your histogram from a dot plot. That's what a histogram is. It's how many fit into a certain range. Okay. Now, this is what we're going to end today on, but we're going to use this data. Okay. So we're going to build a histogram together because my opinion is if you take the time to build these displays just once, it dramatically increases your ability to read them comfortably. Okay. So in 2018, the CDC released the following data showing the rate of adult cigarette use in each of the 50 states and the District of Columbia. This was the one that included DC. I couldn't remember which one it was. All right. So in this case, let's see, where is Maryland on this list? They're in order of lowest to highest. So Maryland is, to its credit, one of the lowest ones in 2018, 12.5%. The highest state was West Virginia at 25%. So I could needle my older sister for that because she lives in West Virginia. Okay. Utah was the lowest at 9%. Okay. So if we're asked to make a histogram and we're told to use a bin width of 2, then our x-axis needs to start at 0, counting by 2s. You'll notice that the very highest state is 25%. So you need to at least build your display so it can go up to 25. I just kept going until I got to 30 because it felt clean. Okay, but if you want to stop at 26 because that's high enough for 25, then fine, whatever. Now, please remember something. Do not think that your y-axis is based off the values themselves. No, absolutely not. Your y-axis is not based on the values. Do not say, well, the biggest number is 25, so my y-axis must need to go up to 25. Wrong. Your y-axis is not the percent of smokers. It's a count. It's how many states fall into these certain bins. So to decide your y-axis, unfortunately, you have to complete a frequency table first. And this is actually why I listed the states in order, to make this part of your life a little bit easier. How many states are at most 1.9%? None. I mean, none of them are 1.9% or lower. None of them are 3.9% or lower. None are 5.9 or lower. None are 7.9 or lower. So the first frequency counts are all 0. But how many states have a smoking rate somewhere between 8 and 9.9? How many? 1. Utah. So that gets a 1. Okay. Now, how many states are between 10 and 11.9? I heard a number that was too high. How many states are between 10 and 11.9? Only one. California, 11.2. Now, the next category is a little bit busier. That's the 8. Okay, so you just went ahead of me. Between 12 and 13.9, I actually got 9. Maybe I miscounted. Now you're making me doubt myself. 12 and what is it? 13.9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 9. Okay. But is everyone understanding where this frequency table is coming from? Okay. Now, in the interest of time, if I gave you time to do this, you would eventually find the most common category is 13. So when you build a histogram, you just need your y-axis to reach up to at least 13 because that's the most common bin. Does that make sense? Okay. So if you do this full thing correctly, this is what it looks like. At this point, you can pack up, but I just want you to have this display done before next class. That's my request. That way we can pick up with this page a little more smoothly. All right, but I'm going to, believe it or not, just abruptly end the recording here. Thanks for watching. Have a good one.